Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. We have been looking at the one-dimensional problem, and then we were looking at how the finite element equations can be derived. So we are trying to generalize it as much as possible. One other quick generalization that is possible that we should do is about the boundary condition. So until just now, we have seen the boundary condition, the function boundary condition, okay, on phi at x is equal to 0. Phi has been described as phi a. At x is equal to 1, we have phi given as phi b. So phi a, phi b were given. Now let us change one of the boundary condition as a derivative boundary condition. So phi at x is equal to 0, phi a, it continues. And d phi by dx at x is equal to 1, that is prescribed. Now the derivative boundary condition. So if we have this, will there be a drastic change in the approach? No, not very much. In fact, all these derivative boundary conditions can be really incorporated into the same approach. So let us just see, to start with, how this is going to change the weighted residual statement. So to start with the weighted residual statement, weighted residual statement is, if you recall, so Wi is the weighting function, and the given boundary condition and the given governing equation is like this. And together with this one, we will also take the boundary condition on Wi prime d phi by dx at x is equal to 1 minus qp. So here, this is, we have taken the boundary condition here of the derivative together with the weighting function here, Wi. And then, so since this is only at the point boundary condition, so we'll put it just as one value. It's not really. So that means that essentially, this has to be validated at x is equal to 1, right? Okay. So the integration of this one, okay, will give you okay, this is the boundary term here, and we have, as usual, this is the same as the weak form. Okay, so this is just the one I copied just about this one. So one thing here is that this first term, which is consisting of derivative as well as at 2 points, at 0 and 1, Let's write it, let's expand this one at x is equal to 1 minus at x is equal to 0, and together with the other terms. Well, phi can be replaced by phi hat. Okay, so these things are repeated here. So what we would like to do is that, as usual, so we are now extreme to this one. So we would like to cancel one of the derivative thing here is about this one. So we can cancel this term here and this term here by appropriately, I'm sorry, this is plus, by appropriately choosing wi prime as minus wi, that's number one. And what else? The other thing is that we will make this, the second term, also 0 and choose and wi is equal to 0 at x is equal to 0. So that way this gets cancelled with this one and this drops down and only this remains with a negative sign here. So there is a minus here and then there is a plus here. It becomes, this becomes minus. So the simplified thing if you want to put it by hat, okay, so we will take this one, wi 2 bar b at x is equal to 1. Okay. So now just to recall, so that means that this derivative boundary condition has been taken into the weak form of the thing, and then this still remains that phi at x is equal to 0 should be phi a. That has to be satisfied by phi hat. Okay. So just to recall, then let phi hat x here be n1 phi 1 n2 phi 2 n3 phi 3 so here, so what is important is that the phi 1 here is prescribed, phi 1 is given to be, this has to be satisfied by a priori, so this has to be satisfied. And another thing you have to observe is that in the earlier problem, so we took the phi 4 also as a prescribed one as phi b, now it is not, and then it is, now it is an unknown quantity. So there are 3 unknown quantities here, right? There are 3 unknown quantities here, and we have to formulate 3 equations. So going by the same logic as we have done earlier, so the whole thing will now come to be, it is the weighting functions will take, we take the weighting functions wi, we will not take n1, we will take n2, n3 and n4. So what is the condition here to take the weighting functions? So the weighting function has to be 0 at the point where displacement boundary condition have been prescribed. So at x is equal to 0, so Wi has to be 0. So that means that it cannot be n1 because n1 takes a value of 1 at x is equal to 0. So it can only be n2 and n3 and n4, which will take a value of 0 at x is equal to 0. So that is why we don't take n1, it's only n2, n3, and 4. So like this, so taking each one of them, so we will get one equation. So that is A21, phi 1. So it looks like this, A22, phi 2. A24. And what else now? So this is on the left side, but on the right side, we have this. So that is N2 QB at x is equal to 1. So this is the thing here. Okay, of course here, don't forget that this is prescribed to be phi A. And then we have phi 2, phi 3, phi 4. However, this, if you substitute phi 1 is equal to phi A, then you take it to the right side. Further, we also have this term here, the boundary term, which is here. So what is the value of N2 at x is equal to 1? So if you recall your shape functions, N2 is, you just recall, so N2 looks like this one. So obviously N2 is 0 at x is equal to 1, right? N2 is 0 here. And so N2 is 0. So because N2 is 0 at, okay. So that is this equation. And we know how to calculate all this K21 and all that we did, right? So just like here, if you want, we can, I think you know that. So we'll, for the moment, we'll skip it. Maybe at the end, we'll substitute those things. So Wi is equal to N3. This also we did. And this also looks like K31, pi 1 bar, K32, pi 2, T3, pi 3, and 3, 4, pi 4. And here also we have N3 QB as prescribed. Again, this is 0, okay, because N3 is 0. Okay, so then the last equation we generate using the weighting function as N4. So here we will use again K41, phi 1 bar, O2, phi 2, O3, phi 3, K44, phi 4, and here we use N4 QB at x is equal to 1. So how much is this value? So if you recall, so N4 is equal to 1 at x is equal to 1. And so this is equal to now QB, right? QB as prescribed by this boundary condition. Okay, this is the this is the derivative boundary condition. So only for Wi becoming N4 equation, so you will see on the right side you have the derivative value. Okay, so like this, so we have we can even generalize it. So another third type. This is the first problem was both function values prescribed. Second one is the right side boundary condition. The third type is we have the derivative boundary conditions at both ends. At both ends, in the sense that we have d phi by dx at x is equal to 0 is qa, and as earlier we have d phi by dx at x is equal to 1 as qb. Okay, so going through the weak form of these things, so using the method of weighted residuals, so this is what we have. So what we will have is that we'll have one more term here. Okay, so if you have this, so I will just use the same thing. So what I'm saying here is that this is the term at x is equal to 1 derivative boundary condition. To that we also add one more term d phi by dx at x is equal to 0 minus qa. So this is also one more term that need to be added because of the boundary condition on the derivative at x is equal to 0. So we know that I think so this gives you two boundary terms here, and I'll just leave it as an exercise. So we will take wi prime, of course, as wi, this is number one, and then we also have one more weighting function wi double prime. So this, well, please, I request you to go through this, trying to cancel this one if you want to cancel this one. So wi double prime should be equal to wi. Okay, so this is what it looks like, and so that this can be cancelled, this can be cancelled, and so the equation, therefore what we have here finally what we get is that dwi over dx d phi hat by dx plus wi so this is wi qa at x is equal to 0 minus so we have only this term earlier wi 2 bar, whereas here we have one more term coming from x is equal to 0. Okay, so that's all only the additional term, and what you get here, if you then here, so we can use the weighting function as n1, n2 or n3 or n4 because there is no boundary condition on the function itself. So we have 4 unknowns. Phi 1, phi 2, all are unknowns here, right? Okay, and then we can take weighting function as, so take wi is equal to n1, n2, n3, 4 to get 4 equations. Okay, so if that is the case, then it's almost a repetition of all these things. Finally, what we get is that we get 4 equations as like this. So it is K11, phi 1, K12, phi 2, K13, phi 3, K14, phi 4, and what you get here is this is obtained by taking the first equation has been obtained by taking the weighting function as n1. So the n1 is having a value of 1. Okay, n1 is having value of 1. So it is simply QA, right? And so similarly you have the second equation doesn't have any right side contribution because n2 here will be 0, okay, either at x is equal to 0 and x is equal to 1, so there is no contribution. So similarly third also will be exactly similar to second equation. Zero, and the fourth equation here is obtained by taking weighting function as n4, so which has a value of 1 at x is equal to 1, okay. So these are 4 equations in phi 1, phi 2, phi 3, phi 4, and knowing this, so we can evaluate all these things. In fact, these final equations here using the boundary conditions, in fact this is the most general thing of all the 3 types of boundary conditions. So for example, in the boundary condition, for example, if phi 1 is given as phi a, okay, so then that means that this phi 1 has to be put as given value, phi 1 is equal to phi a, and then so similarly if phi 4 is given as phi b, then so the 2 middle equations in unknowns and phi 2 and phi 3 can be solved for phi 2, phi 3 using phi 1 and phi 4, right? So like this you can, this is the most generalized way of putting these 4 equations. And finally, in fact, if you look at all these values, so what we can do here, if you put it in the matrix form, so what I have here is that this is a 4 by 4 equation. This starts with 3.11 minus 2.94 and 0 and 0 minus 2.94, 3.11 and 3.11 minus 2.94, 0 and minus 2.94 here, 3.11 plus 3.11. In fact, if you look a little closely, in fact, this is a very important step here, which I'm going to talk about. So here, these things are coming from these four here are the contribution from element 1, and these four element contribution 2, and these four here are element contribution 3. So this is from element 1, this is 2, and this is 3. So essentially what we need to do is that, so we can do element wise calculation of Aij's and assemble it. So what we mean by that is that so this is very important for us. This is N1. Okay, so these are the shape functions. So what it is here is that, so if you go by what is this element contribution of element 1, for example, element 1 will contribute to those integrals only for these two functions, n1 and n2, right? n1 and n2 are non-zero only in element 1. So if you calculate the integrals choosing n1, 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 n2, 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 so that is what is being contributed here, right? So similarly, element 2 will be contributing to n2, 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 n3, n3, n2, and n3, n3. And element 3 will be contributing to 3 and 4. It will contribute to 3, 3, 3, 4, 4, 3, and 4, 4. So that is what is happening here. This is K. So what it will be contributing? So this K matrix for any element, it is 3.11 minus 2.94 and minus 2.94 and 3.11. So what you can see here is that this is a general contribution of any element for this particular application. So what we have, element 1 will contribute to where we have 1 and 2 here. So that means that it will contribute to 1, 1. So that's 3.11 and 1, 2, 2.94 here, and 2, 1, 2.94 and 2, 2, 3.11. Right? And the element 2 will contribute to 2 and 3, that is 2, 2, 2, 3, 3, 2, 3, 3. So that contributes to 3.11 minus 2.94 and 2.94 and 3.11. Right? And then we have third element will contribute to 3 and 4, that is 3, 3 and 3, 4 here. 4, 3 and 4, 4. So this is how it contributes, right? So I hope I will write it here again in some other color, 3.11. So here LO is okay. LO is contributed by 1 and this white is contributed by 2 and this brown is contributed by element 3, right? So if you do the element wise calculations, so it's much easy. So just do the general element calculation and then look for each element. So which are the non-zero shape functions there, and that's where it contributes. So this contributes to II, general term. So whereas that means that 1, 1, 1, 2, 2, 1 and 2, 2. So that's, and we don't really have to bother about other things. They will not be contributed by any element. So for example, if there is a 1, 3 here, 1, 3 here is not contributed by any element, right? It's not contributed by 1, 3, either is 0, 1 is 0 or 3 is 0. So no element has both 1 and 3. No element has got both 1 and 3 non-zero values. So that's how this element matrix is evaluated. So once you have this, so you go back to this one and then substitute. So in the boundary conditions, so it's very important to realize either the function value is prescribed here or this is prescribed, not both. Either the derivative is prescribed or the function value is prescribed. So similarly here, so here this is prescribed or this is prescribed here. So accordingly you choose that if this is prescribed, then this is not prescribed, so you can use that equation. Okay, so let's assume that this is prescribed, okay, and this is prescribed here. So then which are the equations that you can use? Okay, so if this is prescribed, this is not prescribed, so you cannot use this equation. So you can use the other 3 equations and just try to manipulate so that you can calculate phi 1, phi 2, phi 3. So I hope this is clear. Now we went through the whole 3 types of boundary conditions, then we generalized it, then finally we also generalized it how we can do the K matrix calculations in a very simple manner looking at element wise calculations. So this is the procedure which we follow in finite elements. So I hope you have understood. So this is now it's very clear. So now that is K is given. So if these things are given, so you can do the inversion and get the solution. Okay, so I'll stop here. So in the next class we will start the 3-dimensional analysis of finite elements. So but the basic fundamentals are just whatever we have done. So the whole steps are exactly same thing. Only thing is that it becomes 2-dimensional. Of course, a little bit more involved, but all the procedure is same. Okay, exactly how we deal with governing equation, how deal with boundary conditions, weighted residual statements, weak forms, boundary conditions, assembly, everything exactly same. So in the next class, we are going to take up the 2-dimensional analysis of various problems, heat conduction problems, torsion problems, or even stress analysis. Okay, bye for the moment. Bye.